Now let's nerd out with working on conditionals inside Python. So we have a few examples that we're going to describe the output again. So for this first one, we have a simple program that we have the variable red, which has the value of 4. Then we say, and I'm just going to sort of, as I trace through more and more complicated programs, I'll often write red 4 over here to remind me what's in the memory of red. So if red is less than 3, so I'm going to see if red is less than 3, red is currently stored as 4, so red's not less than 3. So we ignore what happens inside that conditional. If red is greater than 3, we say red is now equal to 3. So we change the value from 4 to 3. Then we print value of red, red. And here we printed out a complicated string. So this is something known in Python as an F string, or a formatted string. And this is something you're going to do when you want to print out variables and text at the same time. And the F before the quotes allows you to put variables inside curly brackets and then print out as normal. So Carly, if you don't mind, I would love to see if this code works exactly as we expect. So Carly's going to type this up. I said I think the value is going to be 3 at the end. So my description of the output is it prints out the value of red colon 3 is my expected result of this code.
So wait, I just went ahead and ran that code and it says value of red colon 3.
Awesome. So this is exactly what we expect to see with this string. So second example, puzzle 1b. Here we're going to be flipping a coin, and we have a conditional that's going to print out different things based on the result of this coin. So I have coin is equal to random.choice and choosing between head or tail randomly. And then I have an if statement that says if coin is head, then we print you won, and else we print you lost. So the description of the output is this should randomly, each with 50% probability, print either you won or you lost. And what's interesting is even though we know as a programmer that this is actually determined on a head tails coin flip, the output of this program, we actually have no idea that it's actually a coin flip, because all we're going to see is either you won or you lost. So the output of the program is actually different than what the program is actually doing. That's going to be something we're going to start seeing as we become stronger and stronger data scientists, is often we're focused on what the results are, and the internals are going to be something that kind of gets abstracted away. That this is where you become the expert. You know how it actually works, even though the result may actually only show the high-level information.
Exactly. And I made sure to import random since we're doing random.choice, and I got you won.
Congratulations,
Yay.
Carly. You must have flipped a coin and got heads. Let's make sure this program actually works, and let's run it a few times and see if I ever lose.
I won again.
Congratulations. It's your lucky day. Is it 3 times in a row?
Oh, this must have been you, Af. You lost.
Okay, so it looks like the program's actually working.
Yeah.
So one more example, and this one's quite a bit more of an example, because now we say that data is equal to an empty list, and this means that we're definitely looking at a simulation. So we have a simulation here, the simulation for I in range 1,000, so we're running a simulation 1,000 times, and what we see here is we are guessing a random number between 1 and 10. So we're making a random guess, essentially. The variable is called guess. And if the guess is 7, we're going to record a win of 1. Otherwise, we're going to record a win of 0. Interesting. So basically, what I see here is that essentially this is a simulating game where it's a game where, Carly, you're basically guessing a number between 1 and 10. And if you guess 7, you win. So that's a determination of what I see is happening inside the simulation. And then we append the data to the data frame, data.append is D, and then we say df is equal to pd data frame. Notice that there's quite a bit of indentation here going on, that we have a for loop, everything after the for loop except for the df is indented. And then inside the if statements, we also have additional indentations. So every time we get a guess of 7, we win. Every time we get a guess of 0, we lose. So the description of the program is it's going to create a data frame with all 1,000 observations of a guessing game where we win when we guess 7 in 1 through 10. So what I expect to see is I expect to see a result that has a win-loss record. So I would see a 1, 0, 0, 1, Probably a lot more zeros because I know I'm going to lose 90% of the time.
Right. So when I run that, I made sure to import pandas as PD since we're doing pd.dataframe. And when I just ran the first block of code, nothing happened. I went ahead and typed df, and I see a win column with a bunch of zeros, and at least from what I can see, 1, 1, but there's probably more ones as well.
So it's pretty rare to win this game, it sounds like. Awesome. So we have programs that we looked at the code and we were able to predict what it's going to do. And we saw the prediction actually comes out to be true when we write this code in Python.
Yes, and we could even see how many times we won as well if we wanted to.
Yeah, we can do a bit of analysis. Let's just do this analysis since it's really quick. Let's say df at df.win is double equal to 1. That's going to tell us how many rows we win. And given it's 1,000 observations, I'm expecting Carly's going to see around 100 wins.
Yep, 102 rows.
So almost exactly our expected value.
Exactly.
Now I want to go to a classic problem. So this is a problem that we're going to do a huge amount of simulations and combine conditionals to help us find out more about this problem. So write the Python code to simulate 100,000 genetic tests to test if someone's related to my favorite celebrity, Taylor Swift. The test has the following parameters: a 99% probability that individual related to Taylor Swift will get a positive result, a true positive. There's a 6% probability that individual not related to Taylor Swift will get a positive result, a false positive. About 1% of the world's population is related to Taylor Swift. So now we have to simulate all of the real world parameters on this. So the real world parameters is I see one real world parameter that is whether or not you are related to Taylor Swift. So we know that is a 1% chance. And then what's the other real world parameter here?
So it was also, they said, if you are related, there's a 99% chance of getting a positive test result.
Yeah, so basically the second real world thing here I see there's a test result.
Yes.
So we need to simulate not just if you're related to Taylor Swift, but we need to simulate the test result. And the test result is actually going to be different based on whether or not you're actually related to Taylor.
Exactly.
Because if you're related, the test result is 99% accurate. But if you're not related, the test result has a 6% chance of returning a positive result, while having a 94% chance of returning a negative result, while you only have 1% chance of returning a negative result if you are related.
Yes.
So now we've got this contingency table, and we can program this all into Python using conditionals.
Perfect.
So this is simulation. So I'm going to start with data is equal to an empty list. And then for I in range 100,000 to do the 100,000 simulation of 100,000 genetic tests. And my first real world variable is related. So whether or not I'm related to Taylor Swift is going to be a 1 in 100 chance.
Yes.
So I'm going to randomize a number, and I'm going to say if I get the number 1 out of numbers 1 through 100, that means that I'm related to Taylor in the simulation. So I'm going to say related is equal to random.randint 1, 100. And now I'm gonna go ahead and put a hashtag, which is a comment or a pound sign, and say we are related to Taylor Swift if related equals double equals to 1. So I'm just leaving this comment here because this is the part that I think if you didn't have the context of this problem and you just looked at the code, it might be hard to know what's going on. So I always like to leave comments when we start writing more complicated programs. And then the second bit is if we are related to Taylor Swift, we have a different outcome than if we're not. So I'm going to say if related is equal to 1. And this is if we are related to Taylor Swift. Then I'm going to call this a test result is equal to random.randint 1 through 100 again. So again, 100%, so I'm representing the 100% as 1 through 100. And if I get the result 1 through 99, I know that these are all positive test results. But if I get the result of 100, I know that that result is a negative test result for the people who are related to Taylor. So I'm going to say that if, inside this related is equal to 1, if my test result is less than or equal to 99, so we want to know all of these people from the values 1 to 99. If it's less than or equal to 99, then we're going to say that the final result is related. And I'm going to just have this as a string related, since that's going to be actually what we're analyzing. And then else, the final result is equal to not related. So basically, if the genetic test returns a 1 through 99, we know that if we're truly related, that's a simulation of a related, a positive test result. Otherwise, the final result is not related or a negative test result. And then finally, the last thing I need to do is this related equals 1 at the same level as that if statement. We need to do the else statement for if we're not related to Taylor Swift. So you can see how we're writing a lot more code here. This is the most complicated simulation yet, but it involves a lot more real-world variables. This is real genetic testing. So here we're going to do another test result. So this is a test result of if you were not related to Taylor Swift. Your test results are still a random value, random.randint 1 through 100. But here, the results are 6% of the time we have a positive result. So that's going to be the values 1 through 6. And then the values 7 through 100, those 94 values are going to be a negative test result, that you're not related. So we'll just do this if again, if test result is less than or equal to 6, then we know the final result is equal to related. Else, colon, the final result is equal to not related. So finally, we have all of these variables. We have 3 different variables. We have a related variable, which is whether or not we're truly related. We have a test result variable, which is a number between 1 and 100. That number is not really interpretable because that's just a test result number. And then we have the final result, which is the final result of the genetic test on seeing if we're related or not. So I'm going to accumulate all 3 of these real-world variables. So I'm going to go ahead and continue my code over here and say D is equal to a curly brace. And we're going to say related, in quotes, colon related, to accumulate the related variable. Then I'm going to accumulate the test result, in quote, colon test result, and colon final result, colon final result. So I have all 3 of these variables that I've written in my simulation accumulating, and now I have data.append D, and then outside of all of my indentations, so now we're way back at the beginning, we simply say df is equal to pd.data frame of data. So this was a lot of code, a lot of really nitpicky syntax stuff. So this is where it's so important to run this code right now and really analyze to make sure that we got this correct. So if you run this code, do you get any errors, Carly?
Yes, I did.
Oh, what'd you get?
It says invalid syntax at line 9, which is the else final result equals not related.
So does the else have a colon after it?
No.
So because else is control flow statement, else is always going to have
it. Let's see if that fixes it. And that seemed to do the trick.
And if we type df, what do we see?
And we see 100,000 rows with 3 columns related, and then a bunch of numbers, test result, a bunch of numbers, and then final result. Not related.
So most
Policy are not related.
So most zeros should be not related. We know 99% of the population is not actually related to Taylor Swift.
Yes.
And we know that 94% of the time, they're not related to Taylor Swift. We'll get the result of not related. So now we have a great analysis set of questions. So in our simulation of 100,000 tests, how many people were actually related to Taylor Swift? So if you're actually related to Taylor Swift, this isn't the test result. This is the related column.
Yes.
So this would be all of the rows where our data frame at df.related, so the related column is equal to 1. So df.related double equals to 1 will tell us who was actually truly related to Taylor Swift in our simulation.
So it should say, I think instead of 1, we should say related equals related.
So I think it should be 1 because we did our related simulation way up here is actually whether or not they were related or not.
Oh.
At the very first line of code.
Related equals 1.
So your data frame, your first column in your data frame should be the related column.
That was my bad. Never mind, bad. I did put it in quotes. That's why it didn't work. Okay, never mind. We'll have to say it should be related.
No, that's actually really useful because you put in quotes, it actually interpreted as a string, and a string 1 is not a number 1.
Got
So this is one of these things that Python's really specific about, that if it's a number, it's a number. If it's a string, it's a string. And even though the contents of the string with the number 1 and the number 1 looks to be the same to you, they're totally different.
Amazing. And we got 1,008 rows, so 1008.
1,008 rows, and that is about 1% of 100,000, which
Yep.
is exactly what we expect to see. So 1,008 people out of the 100,000 genetic tests were actually related to Taylor. Part B, in our simulation of 100,000 tests, how many people were tested to be related to Taylor Swift? So now we don't care if they're truly related, we just care if the test results came back that they were related. So df at final result. So we want to know when the final result was double equal to related. So this is gonna look at every single row where somebody got test results back and they were like, yes, I'm related to Taylor.
Yes, and that is 6,912.
Wow. So 6,912 people got genetic test results back saying they were related to Taylor when only 1,000 people really were.
Oh my gosh.
So this is a problematic genetic test.
I can even do 1,008 divided by...
Oh, that's actually part C. You're actually already thinking of the next analysis.
Never mind. Let's
yeah, how many people have tested positive? Well, your answer, let's go ahead and do your statistic because I think it's going to get there. So 1,008 divided by 6,912.
And that gives us 14.583%.
So basically 14.583% of people might be truly related to Taylor Swift, but that's actually slightly off because there may be a few people who were related to Taylor Swift that actually tested negative.
Exactly.
So the third part of analysis says how many people tested positive to be related but weren't actually related. So this will get us close to 14%, but I think we'll get a slightly different answer.
I think you're right.
So this says we want people to be tested to be related, so we know we want a complex conditional. So our first part of our conditional is going to be people who tested to be related. So this is going to be people whose final result, df at final result, is double equal to related. So this is the first part of our conditional, so it goes in parentheses, and we want to know, but actually not related. So we want the and conditional, and they weren't related, so ampersand. Then the second set of parentheses weren't actually related, so this is df.related is not equal to 1. So this is everyone whose final result is related to Taylor and everyone's whose related value is not equal to 1. So they weren't actually related. So how many people got a false positive result? How many people got a piece of paper saying they were related to Taylor and weren't actually related.
It looks like 5,914.
5,914. So that's how many false positives there were. Now if we do 5,914 divided by 6,912, we can get the false positive rate. So 5,914 divided by 6,912.
And that is 0.856.
0.856. So 85.6% of people had a false positive result in this particular genetic test.
Wow.
So-
More false positives than true positives.
Yeah, a whole lot more false positives. So the actual true positive rate would just be 1 minus this. So this would be 14.4%. So just about that rate we calculated earlier. So this is really interesting because we were able to take a very, very complicated problem, genetic testing, and know all the parameters and the statistics of the test, do a simulation of 100,000 people taking this test, and see real world results based on the simulation that we're able to do analysis on and really understand the analysis. So this is where simulation starts really being able to use as a tool for data scientists, because you can actually take real world events and actually have the computer simulate it. And as you tweak parameters, maybe you want to invest more money to make this test more accurate, you can see what the results are by doing simulations just like this. So keep nerding out.